So just in between, let me introduce myself. Hi, everyone. Welcome to the Nanomaterials session. My name is Madina, and I'm actually a PhD student of Professor Daniel Nassim from Bar-Ilan University. And today I'm your session chair. So just a quick reminder for the ones who will be presenting today, you have 15 minutes of talk plus 5 minutes of discussion. So please do not exceed 15 minutes. And I think in 1-2 minutes we can start. So today Ella Sanders from Weizmann Institute of Science will be presenting the first talk. So Ella, I think in 1 minute we can start. So please,
okay,
the stage is yours.
Thanks, should I start? It's like 2 minutes before whatever you say.
We can wait for.
Okay, Monty.
Okay, I think I will mute people.
Okay, I'll start in a minute.
Yes, please. Go ahead.
Hi everyone. My name is Ella. I'm from the group of Ernesto Joselevich in the Weizmann Institute of Science, and I'm going to present my work on electric field and strain-induced polarization in epitaxial cesium lead bromide nanowire. This work was done in collaboration with Yael Sofer from Dan Oron's lab, and it's a joint work. Just in brief about Halides Perovskites, if you've been in the field of materials, you might have heard of these. They've been around for a few decades, but only recently, over the past 10 years or so, have re-emerged as amazing materials for optoelectronics. They have a perovskite structure of ABX, which is A is a cation, B is a metal, and X is a halide. And due to very specific properties of the structure and the lattice, they hold the ability to, they hold very impressive properties in consideration with the optoelectronics, such as high quantum yield, long carrier diffusion length, and high absorption coefficient. And they are well studied and used for very highly efficient solar cells, for LEDs and photodetectors, and many other applications. Halide perovskites are semiconductors, basically. They are a bit different than the classical semiconductors we know, but as such, they hold strain in their lattice. And strain holds a very important role in determining properties of different materials. For instance, here you see the use of strain engineering, where the structure of different layers of perovskite over a bottom substrate of perovskite can really change the structure of the material and thus create highly efficient solar cells and even change the energy of the emission. And in this work, which is done on cesium lead bromide perovskite nanowires, which are the same nanowires that I'm going to present today, you can see that when you grow them epitaxially over a substrate, so the registry of the two lattices creates the anchoring to the bottom, and this creates a very strong strain gradient inside the perovskite. And what we see in this work is that the size of the nanowire really affects the band gap emission, as we can see on this side, which is attributed only to the strain in the material. So the motivation for this work came from the fact that these materials are highly sought out for optoelectronic applications. And when we look at any optoelectronic application, we are bound to have an electric field in our device. And in addition, we are also probably bound to have some strain, especially if we're talking about epitaxially grown layers, which are more and more used in this field. And the combination of strain and electric field on the properties and the performance of halide perovskites has really actually been largely overlooked in the scientific community. It has been studied for regular semiconductors, but in perovskites that are so highly studied, we haven't seen this too much. So this is what we wanted to check. And our studied system is surface-guided cesium lead bromide nanowires on sapphire. So sapphire is our substrate. It's a sheer crystal. It has many different facets over which we can grow the nanowires. And we specifically chose a facet called annealed M. So annealed M is a non-stable facet thermodynamically, which upon annealing in very high temperatures will expose the more stable facets of R and S, creating these nano grooves on the surface. And these nano grooves guide the growth of the crystal of the perovskite, of the cesium lead bromide. You can see this in the SEM image here. You can see the grooves on the substrate. And on top of them, you have the nanowire with its triangular cross section. And they actually nucleate randomly on the surface. This is a fluorescent microscope image, and you can see that they fluoresce in really strong green light. And we take this array of nanowires and incorporate it in lithographically into an array of 2-probe electrode devices. You can see here that the nanowires are placed randomly on the surface, and we can obtain them in between the 2 electrodes. And it's important to stress out that we want no contact with the electrodes, because we want to see what the effect of the electric field is, not of flowing current. Because if we would inject charges, it would further introduce further complexity into our system. And we want to decouple the different phenomena that we see. So we have a nanowire in between 2 electrodes, and our system is an electro-optical setup done in Dan Oron's lab. So we have our sample with the nanowires placed in between the electrodes, and we operate an alternating current over them, and we illuminate the nanowires. The property that we're looking at is the photoluminescence of these nanowires, specifically the change in the intensity of the photoluminescence of the nanowires. So photoluminescence can teach us a lot about the band gap and about the efficiency of this material for optoelectronics. And what we do is that we illuminate with a continuous purple laser that excites the nanowires, which in turn will emit the green fluorescent light. And this can go out to 3 ports into a spectrometer. We can see the spectrum of the material. We can look at a camera. And most importantly, we can collect the emitted photons with a time-correlated single photon counter, which in this way we can retrieve each arriving photon. And when averaging out the data, we can see how the intensity of the photoluminescence modulates with the electric current. So what exactly are we expecting for intensity modulating, PL intensity modulating under an electric field? So cesium lead bromide is known to be a centrosymmetric material, meaning there's no internal dipole. So there's no internal separation of charges. So if we take a material like this and we apply any kind of electric field over it, so the charges will separate, and we will see, we will see an attenuation in the PL intensity. Because the charges are now separated, the recombination is less probable, and we see a decrease in photoluminescence intensity. So when we when we remove the electric field, then we see a rise in the photoluminescence intensity, because now we have more recombination. And this material is symmetric, so we'll see the same thing for the different direction. And we'll see how when there's a field for each direction, we have attenuation, and we don't have a field, we have enhancement. And this way we obtain an intensity of the photoluminescence that is in a double frequency of the oscillating electric field. So if we have this for a centrosymmetric material, to compare to a polar material will have an internal dipole to begin with. So according to the alignment with the external electric field, we'll have either further separation or further recombination, and we can get an in-phase or an anti-phase interaction. So when we came to measure our nanowires, we were expecting to, according to the centrosymmetric material, to get the double frequency result. But surprisingly, we saw this linear result, both in phase and anti-phase. And this was very surprising, since we weren't expecting this material to have any polarity in it. Another important point is that the direction of polarity seemed permanent. We could not flip it, even if when we used oppositional DC fields and even higher magnitudes. The modulation of the PL is very, very strong. You can see the difference between the maximum and the minimum. It's like about 40%, and that is highly used for sensors or any applications such as those. And we also see a small phase between the two sine waves. And this phase can show that there's some kind of transient behavior of the PL intensity under the electric field. So for this, we use the square wave measurement that can show us the abrupt change. And we indeed see the long exponential change in the PL intensity. So we don't see a steady state under an electric field, but rather a jump in the PL and then a slow decay, and a drop in the PL intensity and a slow rise. So this is also seen in very low frequencies. This is 50 Hertz, and you can see it goes well into the millisecond regime of charge carrier dynamics. So we can see two areas. We see one where the external direction of the field opposes the internal direction of the nanowire. As I explained before, this will reduce the separation and enhance the photoluminescence. And then we see a slow drop until it reaches the steady state again. On the other hand, we have the external field direction aligning with the internal field, which enhances the separation, reduces recombination, and we see the drop in the photoluminescence and a slow rise after this. So we see the slow transient behavior of the of the charge carriers. And we try to understand where we see this polarity from. So as I said, epitaxy has a strong role in determining properties of a material. So we did different control experiments. We looked at dispersed microcrystals of cesium lead bromide on sapphire, which have no epitaxial strain in them. And in addition, they are geometrically isotropic, as opposed to an elongated nanowire that could be the reason, the geometry for the separation and the polarity. So in this case, we do see the double frequency of a symmetric material, which is nonpolar as opposed to the nanowires. And in addition, we see a much lower magnitude of the modulation. So this is a strong initial indication that it is indeed epitaxial strain. And another one thing that we try to look at, again, to diminish the geometrical effect, is epitaxial nanoplatelets that do have an epitaxial strain in them, but they are isotropic in X and Y. So we don't have the elongated structure that could be the reason for separation of the charges. And here we again see the polar relation. We see a linear relation with the electric field with the same order of magnitude. So this led us to understand that epitaxy is the reason causing this polar behavior. We went further to structural investigation by low frequency polarized Raman, together with Dr. Tommaso Salzillo from Omer Yaffe's group. And this is a whole world which I'm going to just briefly explain about. When you look at the initial just spectra, you can see in black just a regular bulk microcrystal with the characteristic spectrum of cesium lead bromide. And when you look at the nanowires, you immediately see that there's a difference with the strained nanowires, which shows there's a structural difference. But more importantly, when we look over all polarizations of the incident beam and the collected beam, this can give us an idea of the order of the crystal that we're examining. So a pristine nanowire that does have a difference in structure, but it shows an organized structure. You can see the periodicity every 90 degrees. But the same nanowire that was subjected to an electric field shows a complete breakdown of the structure, breaking the symmetry, which is more resembling of some kind of polycrystalline material. So this led us to understand that that a strained nanowire upon electric field, a strained cesium lead bromide nanowire, will undergo some kind of structural breakdown into smaller crystalline domains, and these will strongly trap charge carriers in the domain walls and lead to some kind of charge separation and the apparent polarity that we see. So to conclude, we see that PL intensity of epitaxially strained cesium lead bromide nanowires strongly modulates linearly with an alternating electric field. And this implies that the nanowires possess a polar structure as opposed to a centrosymmetric bulk cesium lead bromide, as I showed you. The presence of the electric field causes a slow charge carrier dynamics in the nanowires. We saw the exponential decay and rise. And the strong linear modulation is caused by the epitaxial strain, which shows us how important strain is in these materials and their incorporation into functional devices. And this caused a structural change under the electric field that led to the polar structure. According to the Raman results, we suggest that the apparent structural change arises from the creation of smaller crystalline domains in the strained nanowire that was subjected to an electric field, separating the charges and causing the apparent polarity. And with this, I want to thank you very much, especially Yahel, my amazing collaborator, and Professor Dan Oon for enabling this project, Tomaso and Omer for incredible Raman work, and of course my advisor, Professor Ernesto Justelevich, and I'll be glad to take any questions. Thank you.
Thank you, Ella. Wonderful talk. So does somebody have questions? Please go ahead. Questions? So, well, if in case I have one question, actually, I just wanted to ask, what is the band gap just in numbers of your nanowires with and without electric field, applying the electric field?
Okay, so that's a good question. I have a hidden slide for it. So this was one of our estimations that maybe we have a shift in the band gap. So so we wanted to make sure that it's not some kind of shift in the band gap that's making the intensity modulate. So I'll just show you this slide. Sorry. And here you can see that. Can you see the screen?
Yes, yes.
Screen, I guess. And here you can see that when we apply field in, this is the same nanowire, and in black you can see with no electric field, and in blue it's a field in one direction with respect to the nanowire, and in red it's the other direction. So you see that there's no shift in the band gap. It's 525 more or less nanometers. It depends on the exact diameter. But we don't see any Stark effect related shift, if that was your question. It's a pure intensity of the polarinescence that arises from the dynamics of the charge carriers. I hope I answered your question.
Yes, thank you.
No problem.
Any more questions?
I have a question regarding the polycrystalline material.
Yes.
So if it's indeed polycrystalline, you can do micro XRD or something like that and try to see whether or not you indeed have different crystalline facets, right?
So that's a good question. It's not that easy. We could do some kind of GWAX or something like this, but these materials, they're pretty sensitive. And the only XRD work that I know on single nanowires of perovskites is done in a synchrotron, and it's done on a amorphous substrate, because the crystalline substrate will also obviously give you strong intensities. So it's something that it's a good direction of thought, but I don't think it's very feasible. I mean, I agree that the Raman doesn't give us a full picture of the things, and that we indeed would like to understand better what happens, but this is our postulation, that there's a structural breakdown.
Okay, thank you once again, Ella. Wonderful talk.
Okay,
so
no
let's
problem.
move forward. Thank you. The next speaker is Lior from the Hebrew University. Lior, I'm making you co-host right now.
Thank you.
Here. Can you share the screen?
Yeah, one moment.
Mm-hmm.
Share the screen. Let me know if you see the presentation.
Yes, we can see it. Just make it full screen. Yes, awesome. So
Great.
Our next speaker is Lior Asor, as I said, from the Hebrew University of Jerusalem. So Lior, please go ahead.
Thank you very much. So, hi everybody. I'm Lior Asor, a PhD student from the group of Uri Banin in the Hebrew University. And first, I want to thank the organizing committee for allowing me to present a bit of my research, which deals with doped semiconductors and how we implement them in electrical devices. So, as probably most of you know, when we take a bulk semiconductor and we decrease its size below the exciton Bohr radius, we get a discretization of the electronic states in the valence and conduction band, along with increase in the band gap, allowing us to tune the optical properties of the nanocrystals. Now, in our group, we have well-established methods on controlling the size, shape, and composition of colloidal quantum dots for the benefits of various applications. Now, my interest is using the colloidal quantum dots as building blocks for printed electronics, actually using the inorganic semiconductors as building blocks for electronic devices. Potentially, we can build every electrical devices, starting from field effect transistors, which is the most simple device to fabricate, light emitting diodes, solar cells, etc., etc. So, if we take a simple pure bulk semiconductor, let's say silicon, we know it is insulating because the Fermi level lies exactly between the conduction and valence band, unless we do a process called doping, where we introduce impurity atoms that may add holes to the valence band or free electrons in the conduction band, making the semiconductor conductive and is p-type or n-type in relation to whether it has excess holes or electrons. Now, when we deal with nanocrystals, the very small size, reaching about 5 nanometers in diameter, we have very large surface to volume ratio, which leads to an abundance of under-coordinated atoms lying on the surface. These two combined makes the semiconductor nanocrystal inherently conductive, meaning it has excess holes or electrons depending on the material itself. It's still a semiconductor with a defined band gap, but it has inherently free electrons and holes without any further external doping. So our question is, or my motivation for the research is, how can I control the electrical properties of the nanocrystals, meaning the charge carrier type and concentration, which are both fundamental in order to create complex electrical devices. So in order to dope a semiconductor is very challenging. I will just name a few main challenges in the process. So the first one is the self-purification of the semiconductor from its impurities, leading to an expulsion of them to the surface. Okay. The second is the compromising the crystal structure, which may cause changes in the optical features of the semiconductor, which we don't want. Additionally, the impurity atoms in semiconductor nanocrystals doesn't necessarily lead to free charge carriers. Okay, it depends on their chemical connectivity and etc. And the last one, which is the most important for me, is if we want to switch the majority carrier type, let's say from a nanocrystal that is an N-type with electron-rich material, and to make it a whole excess holes, we need actually to overcome the inherent doping of the as-synthesized nanocrystal, which is a major challenge. So just to outline my talk, I will first describe the synthesis of the indium arsenide nanocrystals, and then I will show you my work on the post-synthesis of these nanocrystals with cadmium and the electrical and structural characterization of this material. So to synthesize indium arsenide nanocrystals, we combine indium chloride with 3-methyl-silyl arsine together in a hot injection method. They both react to form the indium arsenide seeds. But in order to further grow the nanocrystals, we need to add the monomers externally throughout the reaction. So as you can see from the absorption of the first exciton peak, as we increase the amount of indium chloride and TMS arsenide into the solution, we grow the nanocrystal until we get the desired size. Okay, and then we purify it. As synthesized indium arsenide nanocrystals are very homogeneous in size, which is very important not only for the optical properties, but also for the electrical conduction, because we must have an overlap between the electronic state between each nanocrystal in order to facilitate the carrier conduction. So with that in mind, I use the as-synthesized indium arsenide nanocrystal and do a post-synthesis process of doping them with cadmium. So the main idea is to use the cadmium as a capping, not capping, as a sort of a shell, in order to passivate the electronic surface states and have p-type doping using the cadmium as it has a lower valency compared to indium. Thus, if it substitutes it, we get a whole addition. So I react the as-synthesized indium arsenide with cadmium oleate under high temperature for a while. And what I see in the optical characterization first is can you hear me? I see that there is a little bit smear on the optical absorbance, but we see a major increase in the PL, which implies us that the cadmium actually sits on the surface and passivating the electron traps, leading to a decreased PL in the as-synthesized indium arsenide nanocrystal. Now, the nanocrystals themselves, after doping, retain their size focusing, and we measured using ICP-MS the atomic ratio of arsenic, indium, and cadmium. As what we can see is, as we increase the doping loads of cadmium, we can see a decrease in the indium signal, which means to us this is the first implication that cadmium actually substitutes indium in the system, and this is what actually we want. The next step, we used atomic resolution STM microscopy in order to map the elements of the sample. And what we can see here is an overlay of the indium and the cadmium signals. We see that the cadmium nicely surrounds the nanocrystals, which leads us to the hypothesis that it really sits on the surface. But what we also can see is that indium and oxygen lies on the same place, that actually we have a byproduct that is probably indium oxide. When we purify these large particles and did XRD, we get the signal that is most likely of indium oxide nanocrystals, which also implies us that indium leaves the system, probably interacting with oleate molecules at high temperatures, forming indium oxide byproducts. So we have two implications. that cadmium actually substitutes indium, which is what we want. The next step is to fabricate the thin films transistors. We do it by spin coating, just casting a drop of the indium arsenide solution, spinning at a high RPM, and doing a ligand exchange in order to exchange the native ligands, which are very insulating, into shorter ones that will facilitate the conduction. We repeat these cycles a few times until we get the thicknesses we want. And then you can see how the nanocrystals are tightly packed on the surface of the substrate. Then we do the method of evaporation. We actually evaporate gold electrodes, interdigitated electrodes, in order to complete the field effect transistor device. Each chip has 6 devices, so we get like an average behavior of each film. This is how it looks like under SCM images. We can see the interdigitated gold electrodes within the tightly packed indium arsenide nanocrystals. So we measure the field effect transistors. I'll start with the indium arsenide, the undoped nanocrystals. We see that the indium arsenide is N-type, meaning we have an excess electrons as expected from semiconductor indium arsenide nanocrystals. But when we measure the cadmium doped ones, we see that we managed to flip the charge carrier, leading to a hole conduction. It's better seen when we do the measurement of the current related to the gate voltage. So we managed to switch the majority carrier type from electrons to holes using the cadmium dopant. Next step for us was to study the structure of the cadmium and see exactly where it lies within the nanocrystal. We did it with synchrotron radiation in New York. We actually we took the nanoparticles and we irradiate X-ray energy in order to excite core electrons. In this case, it'd be the K electron of cadmium, and we follow the absorption coefficient versus the energy. So what we can see here, that the oxidation state of the cadmium in the sample remains cadmium 2+, as we compare it to a cadmium oleate standard sample. We see that the oxidation state remains 2+, which is good for us in order to have a substitutional doping. Next step is we do the Fourier transform for the oscillations in the absorption coefficient, I'm sorry, in order to verify and see the scattering path that the cadmium has, meaning what is the environment or surrounding environment. Actually, we can see the surrounding environment of the cadmium. What we can see is that the cadmium actually has an interaction with 2 species, one with oxygen and one with arsenic. So the arsenic interaction is quite that because if cadmium exchanges indium, it will interact with oxygen, with arsenic, I'm sorry. The oxygen, we think that it comes from the oleate ligands, which somewhat retain in the position near the cadmium. And this is why we have two scattering paths, the oxygen and arsenic. We exchange the oleate ligands with the EDT, and we see that the oxygen peaks diminish, and we see the start of a cadmium sulfide peak, meaning that we managed to exchange the ligand, forming a sulfide bond with cadmium. So with that in mind, we have actually cadmium that sits on the surface. We wanted to measure the effect of the atmosphere on the field effect transistors. So first, for the N-type indium arsenide, we alternate the atmosphere between vacuum and nitrogen or air. What we see is that once we expose the the field effect transistors to air and also for just pure nitrogen, we see a major decrease in the current that is due to an interaction between the oxygen molecules that oxidate the quantum dots. We see also a very large decrease in the mobility. But once we measure the same thing for cadmium, we see that the effect of oxidation is very reduced, meaning that cadmium actually serves as a protective layer on the surface of the nanocrystals, making a stable conduction and mobility. We measured also these samples under XPS. So this is the undoped samples. We see that under inert condition, we see the arsenic peak without any oxidation. But once we expose it to air, we see a major peak of arsenic oxide. And for the transistors, we see that as fabricated, we have a very nice current, while under a urine air, it actually is ruined. And for the cadmium doped system, we see that the arsenic oxide signal is very lower than the undoped. After a year in air, we see that the current remains quite nicely. So just to summarize, we successfully incorporated cadmium into indium arsenide nanocrystals, leading to a switch in the majority carrier type. And we also found that cadmium serves as a protective layer against oxidation, leading to a stable Hall conduction under an ambient atmosphere. So I want to thank my lab colleagues, especially Me'od and Yonatan for helping me with this project. Professor Nir Tesler and Dargesh Tripathi from the Technion for helping me with the fabrication and characterization of the FETs, and Anatoly Frankel and Dr. Jing Liu from New York for helping with me with the X-ray absorption fine structure characterization. And thank you for listening.
Thank you, Lior. It was amazing, wonderful talk. So now we have room for questions. Anybody has questions?
I have a question regarding the oleate choice. So why did you choose oleate? You can use whatever, whatever ligand that you want. And also you have this problem with oxygen. So why not use a thiol or something else to start with?
You mean a thiolated cadmium precursor?
You insert the ligand, so you can do.
No. So what happened?
Start with a different complex.
The cadmium precursor is the one that I use. This is cadmium oleate. Okay, it's the most simple like complex for cadmium to prepare out of cadmium oxide. And I don't know much about different precursors for cadmium, because most of them use carboxylic acid as the ligand for the complex of cadmium. So this is why I use cadmium oleate. But it shouldn't matter, because I exchanged this ligand afterwards with thiol in order to form the film. And
so if instead you use thiols, use a complex with thiols and not with oxygen. This is the question, because then you will completely obsolete the last step of your replacement. You understand?
I understand what you're saying, but I'm not familiar with the thiol complexes of cadmium. This is not really a part of my research, so I'm just focusing on what is better known for cadmium. Now we use, if you're already talking about it, I am using a different dopant instead of cadmium, which is of course toxic and nobody wants to use it. Different dopant that is more environmentally friendly. And with this dopant, I use the different complexes that don't have any oxygen, and it gives really nice results. But I just couldn't show them here because of time.
Thanks. It was a great talk. Thanks.
Thank you.
Thank you once again. Thank you, Lior. Thank you, Ella. So here, I think we're gonna finish with this session. Just a quick reminder, right now we have a tiny break, and then we have a round table with different companies and universities. So please join us. And thank you once again.
Thank you very much.
Thank you.
Thank you, guys.